Hello, everybody. So we're pretty much at the halfway point, almost at the halfway point, I guess. This is the last night of module 4, so module 5 starts on Wednesday. So nice, the halfway point. I guess module 4 actually ends at 5:59 on Wednesday. So just to let you know, on Thursday morning, I will be submitting midterm grades. They don't affect your GPA or anything. As far as I know, the only thing I've ever seen midterm grades show up for is the advisors take a look at them. So if your midterm grade doesn't look so good, your academic advisor might send you an email just to check on things, see how it's going. And I'm a pretty laid back person, if you haven't noticed by now. We still have a few weeks. I'd much rather things be done correctly than quickly. We're very pressed for time, so there is a quick manner involved, but I would definitely prefer correctness over quickness. So if it takes a little bit extra time, that's fine. But I will be turning the midterms in, submitted midterm grades Thursday morning, which means we're about halfway through, rolling along pretty quickly. Got a few more things to go over tonight. Well, tonight's the lecture that was planned for last Wednesday. I like to throw in days like that because y'all have probably noticed that for most of the class examples, it doesn't seem to flow the same way it does when you write code, right? And that's because I prepared these ahead of time. I get prepared and I practice this stuff because oftentimes practice it a couple times because I'm going to be talking and typing at the same time. And y'all know typos show up when we're just typing. So I practice ahead of time, which probably makes it look extra easy in class. So I like to do things like last Wednesday. I always try to do at least one night that is not planned in advance so y'all can see that those typos happen. Code's going the wrong way. Plans get changed midway through, stuff gets shuffled around. It doesn't always go quite as smooth as prepared lectures. And some back and forth things. Couple of main things from last week, I guess, would be stuff from right around break time. We took a break last week. Oh, remember to take breaks, step away, clear your mind, then come back to it. And like we saw after, don't be afraid to erase what's written. Right? Programming is not about typing. Programmers don't make big bucks for typing. It's the thinking. And if you delete everything in that text file and start again, you're not rethinking it. And you're probably starting your typing in a better frame, with a better mindset about it, the problem, than you had to begin with. So don't be afraid to erase the code and start over. So that was one of the main points from last Wednesday. I guess another big point is those auto grading things can be very frustrating. It's trying to match exactly what it wants. There was one way to get the 100% on that. A couple people did get it. But that's kind of why I stopped at the end there, because I don't really agree with the one and only one way to do something. That's kind of counter to everything else that just the basic ideas we're learning in programming. There's lots of ways to reach a solution. There are lots of things that would have been acceptable for those given instructions if I was grading it manually. But computers are making exact comparisons. We saw conditions a couple weeks ago. Right? The computer's just running that through an if statement. If this input gets sent to the program, grab the output. If that's an exact match to this, then that counts as getting the points. But in the real world, there's a little bit more wiggle room. I did go through, there was one assignment that I just kind of completely got rid of. And then one whole section I took out of those programming exercises from the book, and that had to do with the chapter on GUIs, which we'll get to Wednesday. We'll get started on Wednesday, possibly tonight. Graphical user interfaces. A modern look, something with buttons that we can click with our mouse, and then all the text stuff is in the background. Personally, I would have liked to start with those because the text console and stuff, that seems very outdated. I remember when computers went from everything being text-based to graphical user interfaces kind of taking over with like Windows 3, before even the big popular one, Windows 95 came out, or the first little exposure to graphical interfaces a long time ago. I thought we were done with the text-based stuff. But as far as the class goes, I want to be consistent with the rest of Ivy Text as much as I can. It's a prereq for a number of courses. So when you get in those other courses, the instructor is going to expect that you learn certain things along the way. So I want to be consistent with Ivy Tech. The general statewide version of the Ivy Tech shell, obviously I changed it some, is along with GUIs, we're going to look at some other languages. The general statewide shell doesn't do that, but after we cover all this stuff in detail in Python, I want to make sure you can explicitly see why we're doing this, so that you know what a loop is, you know what a selection structure is. So if we jump to PowerShell is one I always do that in. Jump to PowerShell or some other language. I haven't really picked another one yet for sure, but we'll look at some other languages and see that what we studied in detail with Python goes right along with the other languages. They operate in essentially the same way. So we don't have to study all it in such detail for other languages. We just need to see the quick pass of the syntax. And one that I often like to do with that is PowerShell, which is when Windows upgraded the old command prompt stuff back in the 70s and 80s. RAM was a precious commodity, so everything was abbreviated. So we had to remember those abbreviations. Some abbreviations somebody else made up. They spelled everything out, added a modern scripting language, which is very similar to Python. So we'll do, usually takes about 45 minutes to learn the whole language, since we've seen all of it in Python now, or the equivalent stuff we saw in Python. But drifting off there, talking about the section on GUIs, chapter 8. This is the next module. Chapter 7 is great. Chapter 7 uses this thing called Turtle, where you're just drawing lines on the screen. You draw lines and circles and stuff. It's really good practice for working with a coordinate system. In case you haven't seen that in a math class lately, chapter 7 is great. In chapter 8, they're using a proprietary library that I couldn't find all the details, but it's free with the textbook, but it's based off the TK interface package, which wasn't the original one, like the experimental original one, but it was the first one that really took off. And most of our other libraries to build graphical user interfaces in most of our languages are based off the TK interface package. And also is one of the originals. Other libraries are based off of it. It is available in most languages because it's sort of a foundational thing. It's fully integrated in Python. Some of our other languages, we might have to bring in some other stuff to go make it work, but the core TK interface package, which is what your final project is doing, not that proprietary library the book uses that may not be free when you're not in a class using the textbook. We'll look at the TK package. It's available lots of places. It's very easy to use, a good sampling, and it's available in every installation of Python. We don't need external libraries that we have to bring in or anything. So we'll start looking at that Wednesday, maybe tonight. Depends on how time goes, how long this takes, because tonight is something that is kind of important. But one thing, it's hard to see the importance of it when we start out. Oh yeah, before I get started into the next lecture. So that the exercises from the textbook, I took those out of the module. And when you read through chapter 8, like skim through to get the information, but don't worry about the examples, because I use that proprietary library that may not be free after you finish a class using that textbook. So I didn't really want to, I want to go over the basic core part, which is essentially the same. They changed a couple of the names. Like I said, the TK interface package. TK is somebody's initials. He made the whole library, and then when he released it, somebody's like, what about a name? And he didn't have a name, so they just threw his initials on there. He's like, oh, I didn't think about naming it. I've been thinking about what it does. Sometimes as programmers, we get a little focused on the details and forget about the big picture like that. But it was his initials, and it's available in a lot of places. So one of the originals, some things have changed since then. So that's what that other library is. It's sort of more some things that have changed. One of the things that we will see as far as events, there's two ways to do events in the original package. That one of them isn't really used anymore. Being an early package, we learned quickly not to do it that way. So we'll see that starting Wednesday, maybe tonight. Tonight's an important topic though, so I want to make sure there's plenty of time to practice it. Because sometimes it's hard to see that it's in the value of it at the introduction level. So a situation that you might be able to visualize is, well, maybe we're making a payroll calculator. That's a good example. I have a bunch of employees. We need to stick their stuff into data, into some variables that we can work with. So we'll start giving variables names. So we'll have like employee one name. Employee one address. Employee one rate of pay. And maybe we have a few employees, right? You probably already guessed that from the one I was throwing in there. Then we get to the second one, we'll have employee two name. Employee two address. Employee two rate of pay. And so on. Employee three name. And that's probably enough to make the point, ... Obviously, there might be a lot of employees, but we can just keep that naming pattern up or make up something unique. There's different ways we can work with it. You'll see it's kind of a lot of redundancies showing up there, right? All these different variable names, they're all very similar, but slightly different. It would be nice if we could just consolidate those things. And instead of a whole lot of separate variables, kind of consolidate our data into collections. So we'll have like our employee one collection. Then our employee two collection. Is it blurry? The comment in the chat room about the video being blurry.
It is for me a little bit, but I don't know if it's for everybody.
It looks the same that it normally does for me.
It might be just me then.
Okay, maybe it'll pick up, improve a little. It looks kind of clear on my end, but I'm reading everything backwards and stuff. But sort of, it'd be nice to consolidate that data and work in a collection instead of a bunch of different variables. Then we only need one name to refer to everything about employee one, or everything about employee two. So that's what our topic tonight is. It's going to be collections. I might point that at that a couple times. So I'm going to leave that up there, but talk about collections, or for a more technical term on it, we call these data structures. Everybody's heard the term database before, right? We talked about that the other day. There's the things we actually call database, but then there's that technical definition that lots of things fit the technical definition of. The database is storage, long-term storage. where we keep our stuff around. A data structure, on the other hand, is the temporary. That's RAM. That's how we get things into memory, around in memory for processing, and back out of memory to free up RAM afterwards. The term for that is data structures. So databases for long-term storage of them, and data structures for the temporary working with them. Into the processor, around the processor, all the changes, and then back out when we're finished with them. There's different ways we can do that. And at the introduction level, it can be kind of difficult to see the value of these. So I'm kind of a little analogy that I like to use. I've tried different things. I like to go with analogies because it's a good way to visualize things, right? It's hard to visualize an electronic component, so. And it's not just in here, not just this course, that it's hard to see the use of. Like all introduction to software, learning to program, scripting for the server admin people, or people just taking this class to expand their skills. It's hard to see the usefulness of them at the introduction level. So an analogy I like to use is, well, for like a classroom, going to a classroom to do some stuff. There's different ways we can get all the stuff we're going to need. So I have a few things here. Got a textbook for the game development course, folder, textbook for our course, a pen here, might need that, a calculator that could be useful, a pencil, whoops, already dropping stuff, notebooks, some other random papers, another folder here, couple dry erase markers, pick up the stuff I dropped and almost drop the other stuff. And that works to get it stuff from like the car to the classroom, down on the desk, have everything you need here in the file, and navigate around school carrying a small pile of stuff, right? It's not too difficult. It kind of works. But there's a better way. There's right over here. I have a better way to do this, right? That's showing up on the camera. You don't know what that is on the camera. I have a backpack right here. That's a much better way to deal with this. Then instead of carrying all these items separately, which might get dropped, because obviously they're computers as well, laptop, but I usually let things fall, so I don't like to pick up the laptop in the example when I'm intentionally going to let things fall. And just grab all this same stuff and organize it in the backpack. Like the pen, pencil, marker, calculator, stick that up in this front little pocket. All these folders, notebooks and books. Stick those in the big pocket. Zip it up to prevent things from falling. And now there's a much better way to carry all that stuff around. So at the introduction level in programming, not just this course, at every school that teaches introduction to programming courses, it's hard to see how that's useful. At the coding boot camps, it's hard to see the usefulness of it at the introduction level. So think about a backpack, all the stuff you need to carry around the school, carrying it just loosely in your hands versus putting it in a backpack. And the process for when we need something out of that backpack too. When we need something, we open it up, look inside, and check everything in there until we find the one we're looking for. Maybe need a calculator and notebook for the next class. I guess like a math class. So we open this up, grab the first item. Oh, that's the Python programming book. That's not what I need. The next one, that's a folder. Oh, a folder for our own class, so that's not it. Another textbook. Oh, that's not the textbook. A notebook, that'll work. There's the thing I need out of there. Then we can go over here and start looking at the items in the small pocket. Like, if the next item's a pencil, that's the one I need. The dry erase marker, that's not it. Calculator, that's not it. Pencil, there it is. And it just kind of loop through, search through everything in the backpack. Well, I said math class, so the next item on the list of needed things is a calculator. I already saw that in the last loop. I didn't grab it at the time, but start looking through here. There's a pen, dry erase marker, all that stuff in the big pocket. Is this a calculator? Yep, there it is. So we just loop through and ask ourselves that question about everything in the backpack. So that's the power of the data structures, working with collections of things. Instead of a big pile of variables, big pile of data we have to carry around, we can put it in a backpack and then treat it in that much more organized fashion. That's sort of the idea here. Well, actually, I need this. I went very slowly there to express the point of how we're going to program our computers to kind of simulate that analogy I just made. Is when we're actually pulling stuff out of the backpack, we've been practicing that since kindergarten, right? Most of us are pretty quick about pulling the things we need out of the backpack. We know where the things are, and it organizes all the stuff we need to carry to school for a particular day for a couple classes. Our data structures and collections will do the same thing for our data. So, some pictures to draw. I think I try to zoom in and go that way. Oh, that way. Maybe by the end of the semester, I'll get used to the buttons. Oh, whoever set up the remote did stage right and left for the buttons. So always keep pushing the backward one. I don't think I've drawn this picture yet in this course. Have you all seen stack heap diagrams before? These are pictures I like to use to help make sense of what's going on in the computer. Those who've had me in class before have definitely seen these. So on one side, we have a stack, which is a type of data structure. Beyond the ones we're going to look at tonight, but a computer's process off of stacks, which is like plates. After we wash dishes, we get all the dishes clean, dried, go to put them away, we make a stack of plates. And the last plate to get washed and put away is probably the first plate we're going to grab because it's on top of that pile. So that's how computers process instructions. So you may have noticed this before. Whenever you finish writing a script and go to run it, and you get one of the syntax errors because there's a typo, and it's way down on like line 25. You fix that line, and then you go to run it again, and then it finds a typo on like line 10. So the later lines in that script we wrote, the syntax errors get noticed first in Python, right? So whenever a computer processes instructions, it almost always works as a stack. So it reads our Python script in backwards and checks the syntax. So like the first one to go in is the last line in the script. And then it stacks those up till it gets to the first line. And then just like the stack of plates in the cabinet, the one on top of the pile is the first one to get drawn. So then it pulls those instructions off one at a time and runs those instructions to get back through the pile. And the term for that is called pop. We're going to see that word here tonight because that's a common word, so we use it quite a bit in other places. But that's what a stack is. That's one of our data structures. We won't see it tonight. It's a last in, first out type of data structure. And this, in this diagram, will represent our code. A heap is dynamically allocated memory. Dynamically is in that it changes. The computer's going to set aside some spots in memory, in RAM, really, somewhere over in memory, and say, okay, these spots are used for this data, and spots over there are used for this data. And then later, when something big comes in, it's like, oh, there's not enough room between them, so move those to different spots and open up a big space in the middle. But it's memory allocation that can change. So a heap is another data structure, which we won't see this evening, but for those continuing on to a computer science degree or some sort of 4-year computer degree after this, you will spend a lot of time studying data structures, and stacks and heaps will be a couple that you study a lot. Dynamically allocated. So in the picture here, the heap represents RAM. And you'll notice in the picture on the stack side, there's a definite bottom. There's a starting point here, but on this side, it kind of goes off. So I use these pictures a lot to represent what's going on inside the machine. So to start with, let's look at many variables. Did I bring colored markers? I don't think I did. Nope. I didn't bring any colored markers, and I'm guessing the ones sitting here on the desk probably didn't work. Like somebody else left them on the desk. A couple of them I might have left there. But whenever we go to run lots of variables, we'll have our main method or main script, or that is, and it has all our declarations in there. So like for this, I'm going to abbreviate them here, but we might have this data, like E1 name. Then we'll have another variable for E2 name and E3 name. Yeah, that's probably enough for the picture. All of these things in there, but that'll clutter up the picture very, very quickly. And you might recall that a variable is just a named location in memory. When the computer goes and stores that, excuse me, when the computer goes and stores that, well, the computer is going to work all into bits. So there's a big collection of ones and zeros over there representing that data somewhere in RAM. And the computer is going to remember that because by saying, okay, maybe this data starts at bit 8,397 and is 64 bits long. Computer has no trouble remembering that, but a human never will. So that's what a variable is. It's just a useful reference that we will be able to keep track of that refers to that same thing the computer knows by a different name. A good analogy for that is like your own neighborhood. If you're talking to people that live in the same neighborhood as you, you describe it differently than you would to an outsider. And you'd say things like the Joneses house, or the house that used to have blue shutters. And your neighbors are going to know what you're talking about, which building in your neighborhood you're talking about. But if somebody's coming in from California, things like the house that used to have blue shutters is completely useless to them, right? Because the house does, from that description, the house doesn't even have blue shutters anymore. Doesn't give them any information for finding it. So we need the local reference, the things we can say to our neighbors. That's what the computer's doing, because it knows what's going on in RAM. But we're the outsiders, so we need a reference that we can use from outside, such as the street numbers on a house. Right? If we say house 2222, then that's probably written on the mailbox as well as beside the door. House numbers go in order, so even if it's not written there, we'll be able to be able to figure out pretty quickly which houses 2220 and 2224 are, and be able to spot it quickly. So multiple ways to reference the same data, and that's what a variable is. When we have lots of variables, well, they're all separate. They're gonna be scattered all over our RAM. So the computer will know where they're at, they're in there. But it's kind of like the pile of stuff. Might be a better way to do that. So I have a couple common ways we can turn this into a collection. And there's some major differences in retrieval time for the technology we're on as well. I don't know if you've directly encountered it anywhere. There's no examples really springing to the front of my mind right now. But on the old disk drives, they actually had the spinning component. It was much better to have one really big file. That way all the moving components move to that spot on the disk once, then write in all the data. But with a solid state drive, it's better to have lots of small files will get retrieved faster. So there's technology differences as well to consider with this stuff. Not for us to consider tonight, just a preview that is there. Be aware of what you're writing the programs for, basically. Is the idea there. First, we're just going to look at some of the basic structures. And when we start looking at our examples, really it's going to be a way to kind of consolidate our naming. That's the most useful thing at the introduction level, is instead of having a whole bunch of variables with similar names because they all refer to the same employee, or similar names because it's about employees' names or about employees' addresses, then we can consolidate that to just one naming convention for all the similar data. And that's the two we're going to think about here, not the differences between a disk drive and a solid state drive if we need to have this stuff from long-term storage somewhere. But how do we want to organize this? Like we could put all the employee 1 data in a collection, then have an employee 2 collection, employee 3 collection, or we could split it up by data type. We could have a name collection, and then our indexing, how we refer to it, we could have the numbers there. The first thing, second thing, third thing, and the name collection, or then the address collection and the rate collection. So it's sort of an organization thing to help clean up your code and organize this kind of the way to think about it. And in the long run, keep the backpack example in mind. Instead of carrying around a big pile of data, we're putting it in a nice little, putting it somewhere that's much easier to work with. But that easier to work with part is hard to see at the introduction level. So we need the syntax and collections, because it doesn't get any smaller, right? If we need to store this data in a different way in memory, like into one big collection, we don't lose any of the data, because then we would have different data, right? What we would do is just put it into a more organized spot. So at one spot in memory that has all of those bits instead of several small spots scattered around. Which both of those have different advantages. And don't confuse that with the solid state SSD thing, the SSD versus disk drive thing I just said, because this is RAM. The difference is between DRAM and SRAM, and the difference there is how long it lasts. One of them is more expensive and will essentially last forever as long as we keep supplying power to the machine. And the other one is cheaper, but we have to use extra power to keep refreshing it because it doesn't last as long. One's more volatile than the other, but we're not really going to lose that in. Generally, we're talking like 20 minutes before like at the SRAM, if something happened and we didn't refresh the data that was in there, it'd be like 20 minutes. So it'd be a really, really big program before we just lost the data that we were working with. So it's really quick that way. This is RAM, not storage. But it organizes it into one chunk or a more organized chunk so we can more efficiently make use of our space. There's different ones. And the first one we're going to talk about, is it okay if I erase over here? That intro example. I see some head nods here in the classroom. That was just the lead in. So that's what we're going to try to get away from. And yeah, that I already pointed at the other thing I wanted to point out with it, which was which way makes the most sense to organize that. The first one is array. I have the technical definition wrote down if I don't know it off the top of my head. So an array is memory locations allocated to store the same data type. My line breaks in a bad spot there. We'll get back to it. Memory locations to store the same type of data sequenced by a recursive algorithm. So we'll stick the same type of data and use a recursive algorithm, which means we're going to use the same algorithm over and over again. So to put that in the stack heap diagram, maybe I'll redraw that one I had. The first thing that we put in this collection of data instead of separate variables starts at, I can't remember what I wrote earlier. Humans are going to forget those numbers, right? It's going to start at bit, say, well, I'll just do 1,000. That'll make the math easier. And is 8 bits long. So they're all the same type of data. So they're all going to be the same size. We know where the starting point is. So a recursive algorithm means we're going to use the same algorithm over and over and over every time. So maybe we'll have something like 3 times the starting point. 3 times our data size plus the starting point. I can't seem to spell things correctly today. So we know we're going to start at bit 1,000. Everything's 8 bits long, so 3 times 8 is 24. So then somewhere over here, so if that's 8 bits long, it's 1,000. 1,001, 2, 3, 4, 5, 6, 7. And then from bit 1,008 up to 1,024 is still open to do other stuff with. Then we have these bits. Then our third thing, again, 24 times this, it's going to be 24 bits over from the start of the previous one. So then the next one's up at bit 1048. We don't need to worry about this stuff too much in here. This is just going over the definition of what an array means. We have this recursive algorithm that we use over and over. Which I should point out that in the modern world is pretty much always +1. So if we have 8-bit data, our recursive algorithm is +8 from the starting point. The old definition had more complicated ones. When this definition was set up was back in the days of the heating coils used to melt mercury switches and feed power into vacuum tubes to amplify things. So back then, we didn't want to turn on a bunch of memory locations right next to each other. because that meant turning on heating coils right next to each other, which became a fire risk. So the definition was like this, but in the modern world, it's pretty much just always +1 because not so much of a fire risk with the current process, modern processors. Not like there was in the 1950s when this definition would have been put together. But it's still the same definition. That's a better example of recursion than +1. So that's what an array is. But from what we've looked at with Python, does anybody notice something that doesn't quite seem right there with Python? Like it's not quite doesn't fit with everything we've seen in Python. If we have some data to store in Python, what do? We'll say like our variable name equals our data. Maybe it's an integer. Maybe it's a string.
Python does the work of figuring out what kind of data it is for us, right? We don't have to tell it ahead of time.
Yes, so this one right here, the same data type. That doesn't really happen in Python. We're not restricted on data type. So like in C++, if we wanted to store this data, we'd have to explicitly say, we have an integer, we're going to call it X and assign it the value 4, end of instruction. But we said it's an integer. We cannot change that. If we want to change that into the character 4 so that we can print it to the console, we have to create another spot somewhere that is actually turn that into a character. Create a spot in memory to turn that into a character. So we have to say what it is explicitly. In Python, we don't. So this same data type kind of definition fails. So we don't actually have arrays in Python. But that's another one of those technicalities. Because array is also the term, that's our fallback term to use when we're talking about these. Kind of like, we don't say go to a search engine and enter it in the filter. Right? We don't say search engine or search filter. We say Google it. Or we want to record a TV show. We don't say use the digital video recorder. We don't say use the DVR. We say TiVo. Right? Those words that are kind of specific examples that took the place of the actual name on things. An array has done that for data structures. The main reason being the rest of the things, stack and heap, or the one we're going to use the most often in Python, that's what I'm going to talk about, is list. List especially has a lot of preconceived notions, right? That thing I started with up here, that employee example, that was a list. It was a to-do list, grocery list. We have a lot of preconceived notions about the word list, which are different than programming version of a list, right? So array is the word we generally use to refer to things, even in languages like Python, where we technically don't have an array. Just because it doesn't really show up outside of computer programming like list and stack and heap. Then there's another one that's going to show up tonight. In Python, we call them dictionaries. Some languages, we call them maps. It has different names in different languages. We'll look at that, see that in a little while. But a lot of the words have other uses we might have a preconceived notion about. So that's why array is generally the fallback term. It's okay if I erase the definition of array? Just remember that it's memory locations for the same type of data stored via a recursive algorithm, but pretty much in the modern world, since everything's the microchips, lots of transistors on a thing that are using very small voltages, it's not a fire risk, so we go with the easy recursive algorithm of just +1 every time. The one we do have in Python is a list. This is a very common one we have in a lot of languages, and it's very, very useful. I have a note here while I'm pointing at things I might as well do this before I erase this. Notice where I pointed at the start bit here. The start there, we have 8 bits, which ends at 1008. And so our last bit would start at 1007. And our indexing is often a little off from that. You may have encountered this before. The reason is we ask for the beginning and count from the end. So when we want to ask for this data, we have to come to the very beginning. So that is our starting point plus 0 bits. So ask for the start plus 0 bits, but we don't actually have that last bit until we get there, right? So our first bit, if it's 8-bit data, starts at 1001. Second bit starts at 1002, but we don't actually have that second bit till we get to slot number 1003, right? Until we've read it in. So we start at 0 when we're counting, ask for the 0, and count from the end, which is after the bit. So we'd say there's 8 bits because that 8th bit ends at 1008. Or yeah, we want to read in all the data. We don't have that piece of data until we get all of the bits in. So there's that discrepancy of the numbers we're counting from and where the end of it is, which is also different language to language. So you have to know which language you're in, because some languages start at 0, so they don't have to change anything. We don't have to do anything to get to the starting point. Some languages went ahead and modified that to go with the more intuitive 1, what humans are used to counting with. And some languages start at 1 because they have extra data to include. For example, SQL includes extra data. So that's something we'll see a lot. We work with multiple languages just to optimize what's going on. And it's very, very common that we'll be working in Python or Java or PHP and interacting with the SQL database, a relational database. So our SQL code, when we use the SQL portion of our scripting, our indexing starts at number 1 because the database includes extra data there, the headers and the headers for the columns, the numbers for the rows, some extra data, background data that the human doesn't need, takes up that first index. So we start at 1 there. But a lot of our programming languages, those I just mentioned, all start the collections at 0. So we have an off by 1 issue to deal with. Which again, it's just a freebie thing. It was in the next slide of my notes and it fit that picture. So that's why we got started 0 instead of 1. Ask for the beginning and count from the end of the data. So the next one, a list, is a little more open and dynamic to work with. That's what we actually have in Python. We have lists to work with. You can store a countable number of mixed data types. Do I have the actual definition of list here? Nope, I didn't write down the formal definition. So memory allocated to store different data types sequenced by a pointer. So each will store a bunch of data, doesn't matter what kind it is. Our first element That's our term for the things in a list or an array or a stack or whatever we're working with, a queue, priority queue, a heap. They're elements of data. So each one also includes a little bit extra data pointing to the next thing in the list. So instead of a recursive algorithm, we don't need that fancy, don't need to do a whole bunch of math to figure out where our next one is, because each one of our pieces of data, we just tack a little thing on the end that points at the next piece of data. So maybe this is the second element. So at the end of the first element, we just stick something at the end and says, our next element is over there. Oh, Santos is back. His connection's better now. Hi Santos, is the video better now?
Yeah, a little bit. I think I'm having problems with my internet.
Oh yeah, that does happen sometimes. Everything's being recorded, so you can take it back. But this is very similar to the lecture I gave in SDEV 120, which you heard about 6 weeks ago, I think.
Yeah, I kind of remember it.
It was near the end. Very similar lecture. So we just got up to list. So instead of that, having to do a bunch of math to figure out where the next one is, each piece of data includes a pointer to say, okay, the next piece of data is over there. Then we'll start at the beginning of that, get over to the end, and then there's a little extra bit tacked on the end, says the next piece of data is down there. And it allows for dynamic things to happen. It's a lot more dynamic. We're not, with that recursive algorithm, the math is calculated for where everything's going to be stored every time. So if we want to get rid of something in the middle, we have to recalculate those positions for everything afterwards. If we want to get rid of the first element in our array, we have to recalculate the positions in memory for every single thing in that array. So arrays are typically used when you're working with a language where we do have arrays. It's typically used for things that aren't going to change. We will see that in Python with tuples, which is added in Python as a way to more of a protection thing. We can't change our data as a way to protect it instead of the allocation, because internally it's like a list. Because there's a lot of things we could do, right? If we don't want this one, well, an easy way to deal with that is just go in and modify the pointer. Say, okay, now our pointer is going to say the next piece of data is over here. So this piece of data is no longer in our list because the previous thing doesn't point to it, it points to something else. It's not used anymore, and before long, garbage collection will grab it. So one thing about Python is it has really nice garbage collection. Whenever we're done with things, we don't have to manually delete them. We recognize when we're finished with them like we would in C++. That's built into Python and handled in the background. So we can remove an element from a list just by pointing somewhere else. And our last element, there's no place for it to point. So whenever we walk through this list, and when we go through everything in the list, we'll just start looking at elements, grab this data, see the pointer, goes to the next one, grab the data, grab this next bit of data, and then that last pointer goes off to nothing. Our term for that's null. Less than nothing, because we have zeros everywhere, right? Talk about ones and zeros, but the zero means something. The null is sort of less than nothing. It's emptiness. So when we hit a pointer that points at nothing, we know we're done. Or if we want to add more data to our list, we can just change this pointer to, instead of being a null pointer, to point to this new piece of data over here. And it's more dynamic. So lists are a lot more common to use, but we typically use the word array when we're talking about them, just because list is going to have preconceived notions. but they behave differently. The dynamic part's nice. We don't have to delete the whole thing and recreate it just to make little changes. We can mix our data types, which is important for Python. And from a programming perspective, they'll essentially look the same. Once we create, after we create it, we interact with them in very much the same way. And an important word for the ones we're going to look at tonight is countable. And that doesn't necessarily mean that they all have numbers. Because one of the ones we're going to look at, we don't even use numbers on it. Iterable is another one. It means there's a finite number. There's a definite beginning and an end. We won't look at sets, but sets are dynamically allocated. They change on us. We don't even know what order the data is in. The computer's going to periodically, the Python programming language is going to stop and rearrange our set on us. So we don't know which one's the first element, which one's the last element. We just have a bunch of elements there, which obviously can be a lot faster because we don't have to keep track of what order they're in. We don't have to keep them in the same order. I don't know if we'll see that one or not, but it would change on us. But it is still countable, which really means finite. There is a definite beginning and an end to it, even if that order is going to change automatically on us. Or another way to think about it is, remember, machines don't know what numbers are. That's a human concept. So a machine has no idea what the first or last thing is. It doesn't know the difference between a 0 and a 9. It relates that to a pattern. So it's a human thing. Yeah, which I guess I'm skip to the bottom of this page of notes. In Python, we have our for loops are actually for each loops. They're for working with collections, data structures, or text files, or anything where it has a natural iterability to it. There's naturally iterable lines in a text file, elements in a list. There's a definite start and an end and a clear separation between each one. So that's what we have in Python with our for loop. So it makes it kind of nice to work with. So lists are very dynamic. It's kind of a nice one. We also have tuples, which are essentially like a list. We'll see the syntax for it before long. We'll use parentheses when we create it instead of square brackets. So we'll see the syntax after a break here very shortly. And I believe everybody saw arrays and lists in the SDEV 120 class, right? I know a number of you all have been through the class. I see head nods. I know it's at the end. It used to be like all the way at module 8, so we would get cut off, and I think they moved it up to like module 6, so it doesn't get dropped as often now. And now it's like files, writing files is the last thing, everything falls behind.
I lost audio.
I'll turn the cameras, so you can see them sitting there doing stuff.
That's better.
The good speaker made a sound. Can y'all hear me now?
Yeah, I think so.
Much better.
Sorry, I don't know why it does that. The cables ran through the wall. It's a professional installation. They seem okay where they come out of the wall. I clicked around on some stuff, went to device manager this time, but I don't know if that's really doing anything.
Maybe it's hooked in the motion detector with a,
Yeah, but I don't know. It seems to do it every night, so as long as there's a signal so that you can make me aware very quickly. So we were talking about list, tuples are very similar to list. So list, we're gonna use square brackets for. And a tuple, we'll use parentheses when we create it. So this is creation. We'll see this after a break here very, very shortly. And when we ask for an element, we use square brackets on both of them. We'll see that afterwards. And we give it a number because these are sequenced. They stay in the same order. The one we say is the first one will stay the first one until we change it for list. And tuples are non-dynamic, which means we cannot change the stuff in a tuple. So I guess at this point, the big thing there is it'd be like sort of a protection issue for our data. We can't accidentally change our data. But otherwise, working with it is almost the same as a list. We're just passing an index. We're also going to see dictionaries tonight. Which are very similar. We use curly braces when we create them. But they have key value pairs. So sometimes they're known as associative arrays, which is a term that I like because it helps to describe what they are. Instead of using numbers to ask for it, we don't ask for element 0 or element 3. We assign a word to it. So in that earlier example with the employee name, address, and rate, instead of calling those indexes 0, 1, and 2, and then remembering that, we can assign it to index name and index rate, and index address. And it makes it a lot easier to keep track of our data that way. We'll see some syntax on that after the break. I think that's everything I had in my notes. Let me double check. Let's use square brackets, tuple use parentheses, dictionaries use curly braces. When creating them, we use square brackets to access them on all three of them. Simple examples, and yeah, that's the end of those ones. So, looks like we've been at this a little over an hour. Seemed like a good time to take a break. 10 minutes sound good to everybody?
Sounds good.
So we will get back to it. I'm looking at this machine because every clock I can see has a different time on it for some reason, which is odd. It says 7:05, so we'll get back when this clock says 7:15. We'll see y'all in just a moment.